So now we're going to start looking at some applications of derivatives. So one of the first big applications of derivatives actually comes in evaluating limits. So it seems a little bit backwards because the derivative is defined via a limit, but this is known as Lhopitals Rule. Okay, Lhopitals Rule. And specifically, it allows us to evaluate limits of the form, the limit as x approaches a of f of x over g of x. When this limit gives us some kind of indeterminate form, specifically 0 over 0 or infinity over infinity. So let's write out the rule in full first. So suppose f and g are differentiable functions over an open interval containing a except possibly at a if the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0, then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. Okay. So if we evaluate the limit and we get an indeterminate 0 over 0, then we can then take the derivative separately of the top and the bottom and then retake the limit. And then that might give us an actual answer. So if you remember, 0 over 0 form usually implies that we can do some kind of algebra to evaluate it, but that's not always the case. So this is an alternative if the algebraic methods don't work, or you could just skip the algebraic methods and jump right to this if taking the derivative is easier. So note that since these functions need to be differentiable at a, they also will need to be continuous at a. So using the continuity at a, it's pretty easy to go through the proof of this. So definitely something I would recommend going through. And there's a nice proof of it in the OpenStax textbook as well, if you need help to reference it. But I think it's a good idea to try to start trying to go through some of those on your own, some of those proof ideas. So let's look at some examples first. And like I said, this also works if you get infinity over infinity. So we'll modify it for that case as well. But first we'll look at some examples. So one of the easiest, not easiest, but most common examples for this is the sine of x over x example. So in Math Tools 1, we looked at how to show this using the squeeze theorem, I believe, or at least like the outline of it. But it's actually a lot easier to do it with Lhopitals rule. So again, if we do direct substitution here, we get 0 over 0 because sine of 0 is 0. So what we do is we go ahead and say, okay, let's take the limit as x approaches 0 of the derivative of the top, which is cosine of x, and the derivative of the bottom, which is 1. Cosine of 0 is 1, so when we plug the limit in, we just get 1. Okay, so a much easier approach than using the squeeze theorem. Okay, so note that up here in this definition, usually when we use a, we're not including infinity, but there's no restriction on that here. A can be infinity. So we could look at the limit as x goes to infinity as well. So let's do that. Let's look at the limit as x goes to infinity of e to the 1 over x minus 1 over 1 over x. Okay. So first we'll go ahead and take the limit of the top and the bottom. So the limit as x approaches infinity of e to the 1 over x is going to be 1. That's because the limit of 1 over x as x goes to infinity is 0. And e to the 0 is 1, right? So it's going to be 1 minus 1 on top, which is 0. And then, like I said, the limit as x goes to infinity of 1 over x is 0. So we get the 0 over 0 indeterminate form. So now we can take the derivative of the top and the bottom. So we'll need the chain rule here. We'll get e to the 1 over x times negative 1 over x squared minus 0, because negative 1, derivative is 0. And this is negative 1 over x squared on the bottom. Note that these cancel out. So this is the limit as x goes to infinity of e to the 1 over x, which is going to be 1. Okay, so now I don't think we necessarily need to write this whole thing out again. We could just say modify this to say that this could also be equal to infinity and this equal to infinity, and then it'll still be true. But we specifically have to have infinity over infinity. Okay, so we can't have any other indeterminate form. We can't have 0 over infinity. We can't have 0 times infinity, infinity minus infinity, 0 to the infinity, 0 to the 0. There's a lot of indeterminate forms, but this specifically is only working if we have 0 over 0 or infinity over infinity. And a negative infinity is fine. So we could really write plus or minus infinity and plus or minus infinity. It doesn't need to be the same infinity on both sides either. So the negative doesn't really affect it here. So let's look at some examples with that in mind now. So if we just look at a normal old rational function, the limit as x goes to infinity on this would correspond to the horizontal asymptote. So if you've looked at how to do this before, you know that you would force factor, right? And you would force factor out an x, and you would end up getting 3/2 for the limit. So this is just an alternative way to do it. You can still do it that way, of course. So if you plug this in directly, you get infinity over infinity, right? 3 times infinity is infinity, plus 5 is still infinity, and same on the bottom. So now we're going to take the derivative on the top and the derivative on the bottom. So we get 3 on the top and 2 on the bottom, and that's just going to be 3/2. Okay, so a lot simpler than force factoring. So this is a really helpful tool to be able to do these kind of limits very quickly. Okay. All right, let's try the limit as x goes to infinity for the natural log of x over 5x. Okay. So again, we'll get infinity over infinity first of all. So then we take the derivative. We get 1 over x over 5. Okay. And we don't even need to simplify. We could just go ahead and do it now. The limit of 1 over x as x goes to infinity is 0 over 5. So that's going to be 0. Okay. Okay, so let's look at now the limit as x approaches infinity of x squared plus 5 over 3x plus 4. Okay. So if you recognize this rational function, you'll recognize it as one where there is no horizontal asymptote. So this implies that there's not a limit as x goes to infinity, at least not a finite one. So what's going to happen here? Well, we still would get infinity over infinity if we just plug it in. So Lhopitals rule can still be used. Okay, so now when we do it, we get 2x over 3. And now we just get infinity. Not infinity over infinity, just infinity, right? Because it's basically 2/3 times x, which in 2/3 times infinity would just be infinity. So that's all that we would do here. This just is the limit, right? So the limit as x goes to infinity of that original quantity, x squared plus 5 over 3x plus 4, is infinity, right? Which means it doesn't exist, but infinity still gives us more information. So we would still write that it's equal to infinity. Okay. So some other notes here. This does work with one-sided limits, and you can do this more than once. Okay. So if you get an indeterminate form a second time, when you take the derivatives, you can then do it again. Okay. So some easy examples of that would be if we do something like the limit as x goes to infinity of 3x squared plus 9 over 5x squared minus 4. Okay. So that'll be infinity over infinity. When we take the derivative, we get 6x over 10x. So we still get infinity over infinity, right? So because we got it again, we can just apply Lhopitals rule to this quantity now. Okay. So we get 6 over 10, which is just going to be the limit, which is 3/5. Okay. So you can keep doing it more than one time.